before we can get to spin, let me show you, start the talk with a song, okay? It's the quantum song. Turns out one group figured it out and made a song dedicated to quantum mechanics, okay? None of my friends, by the way. I wish they were, okay? But here it is. It's the quantum song, I call it. And the guys call it superposition. We talked about that the other day. Superstition aims with imprecision. But when things can't be explained, superposition. Oh, I love that song. Yeah, my son pointed it out to me. I thought I'd bring it up, so go find it. It's called Superposition by Young the Giant group out there. And they say, but when things can't be explained, when the mathematician cannot explain to you, they just say superposition. More or less like Mary Poppins. You know, when she couldn't explain something, she would say supercalifragilisticexpialidocious. That's how it works. You know, when you don't know, just say, I don't know, say something like energy, and that'll fix all the problems. So what is this superposition? Well, I covered it the other day, okay? And it's, you know, a horse stands still and it also runs at the same time. Okay, so I don't know, maybe, maybe not, okay? Okay, so what is this spin thingy? Well, one of the visitors to the site here put this comment out there. He says, electrons do not spin, PBS space-time, okay? And I go in there, look at the video he referenced, and had already the idea of doing spin today, so it just came in very handy, and just coincidentally. And you go in there, and Matt O'Dowd, the guy who does the PBS physics, mathematics program, he says the following thing. It says, think of electrons as being connected to all other points in the universe by invisible strands. And you see it there, he illustrates, not this, but this. Huh? Let me read that again. Maybe I didn't read it properly. Maybe it went over my head. Let's see. Think of electrons as being connected to all other points in the universe by invisible strands. Okay, and the fellow makes a comment, says, it's staring them right in the dumb faces. Okay, so we're supposed to look at this as strands that somehow bind, interconnect. What did he say there? Connected to, right? So he's saying that, yeah, these strands are connected to every, I guess, atom in the universe, to all other electrons in the universe. That's what he wants you to think. Where did he get that? Okay. And here this is what he illustrates here. And so you ask, well, what are those ribbons? You know, I mean, where did he get that in quantum? Quantum was a particle theory. You know, you have these little dots, balls, corpuscles, grains of sand, grains of dust. And suddenly we have this interconnectivity. Suddenly, you know, all electrons are connected to all others, or to atoms, or to whatever matter is out there. He asks you to think of it that way because that's what they observe but don't observe. They can't see it, but this is the conclusion they arrive at by saying you're supposed to think of it that way. Okay. This is what you know, this fellow is not the only guy who said this is what I see out there. These are some of the statements, some of the testimonies you'll find out there in the same line. Here you have Michael Disney, and he says, but the electromagnetic theory is not based on action at a distance, as was Newton's. Space is thought of as being threaded throughout with electrical and magnetic tensions. Dara Ebbing, he wrote an important book, General Chemistry. He says, a chemical bond acts like a stiff spring connecting nuclei. As a result, the nuclei in a molecule vibrate rather than maintaining fixed positions relative to each other. So the first guy says everything seems to be threaded throughout. The second guy says you got to think of it as stiff springs connecting nuclei. What did Matt O'Dowd say? All electrons are supposed to be thought of as being connected to something out there through some kind of ribbon, I guess. Here's the Casimir effect. A field in physics may be envisioned as if space were filled with interconnected vibrating balls and springs. And there was a conference at the University of Colorado known as Electromagnetic Waves, Physics 2000. It says wiggling one charge causes the field lines attached to it to wiggle. And after a time, the other charge starts to wiggle. It's just like a rope connecting two rocks. The wave here consists of a wiggling line of electric force, which you can think of as being attached to the vibrating charge. Okay? So we seem to have not only one fella, but here we have at least several testimonies from professionals, people who supposedly are mathematical physicists if you want to call them, and these people are saying that everything is connected, but that's not quantum. But what quantum says. This is what quantum says. Okay. Well, this is first. This is our hydrogen atom. You can see it's connected to everything. You have the atom in the center. Okay, that's the center of the very center there. That's the conversion of all these threads. That's going to be the proton. That's the center of the hydrogen atom, and then the hydrogen atom has this shell, this membrane, okay, this balloon that encapsulates the proton star, and that's going to be the electron shell, which pumps back and forth. That's the quantum jump, and by doing so, it torques the ropes. What ropes? All the ropes connected to it from every atom in the universe. So what these people are saying is that you have to think of it as this, but that's not what they illustrate. That's not what they believe in. That's what their mathematics addresses. What their mathematics addresses is something totally different. Okay? They talk about, individual particles. And so here's the difference between them and us. This is what quantum proposes. Discrete particles. We are the ones who are proposing that the atoms are interconnected. Where did quantum now come up with the idea that atoms are interconnected, and what is the physical entity that interconnects them? I mean, they have to identify them, but see, what they say is something different. They say you have to think of it as if. You're supposed to visualize it as if, but that's philosophy. That's not part of their physical interpretation. Physical interpretations is always particle moving through space, little ball moving through space. That's very different than saying that all these electrons, atoms, whatever, are connected, physically connected. Where is the connector? Where do we see that in the standard model? Okay, so it's cheating because they throw this out, but then they don't follow it. They don't say, well, we believe that everything's interconnected. They don't say that. They just say, you got to think of it as if. So it's the language that, is really killing them there. Okay, what does Matt continue? He says, quantum mechanics has lots of weird stuff, but there's one thing that everyone agrees that no one understands it. I'm talking about quantum spin. This elusive little behavior of the electron. Spin? Well, spin. There you see it spinning. There's an electron spinning. That looks simple to me. I mean, why is this so mesmerizing for Mr. Dowd? You would think that he would understand spin just like I understand, or like anybody else understands spin. There you see it, right? But these people are saying that that's not spin. In other words, that's not at least how an electron spins, okay? So how does an electron spin, or what is a spin? And that's the question Matt asked. He said, what is spin? Well, you would think it's like that top there. We all understand spin. You just twirl the top and we understood spin. And Matt is saying, well, we're going to try to find out. He spends a whole show there trying to explain what spin is when it's very simple. There's a guy who also has like 6 videos, hour videos, like 6 hours talking about spin. I mean, spin is spin is spin. You take a top, you spin it, we know, right? Why is this so difficult? And so we have to look up what spin is, and we go to the Wikipedia. And here we find, which, a lot of these guys use anyways. Okay? And so what is spin? Well, here you see it. It says spin, an intrinsic form of angular momentum. Carried by element, carried. They carry it on their back. The angular momentum. I like the words that mathematicians have to use, that have to invent the phrases they have to make in order to make their physical interpretations. So they carry the angular momentum, which is carried by elementary particles. Okay, I hope you understood. It carries it. Okay, composite particles, hadrons, and atomic nuclei. Okay, spin is one of 2 types of angular momentum in quantum mechanics. The other being orbital angular momentum. Orbital angular momentum, what is that? The quantum mechanical counterpart to the classical angular momentum of orbital revolution. Okay, there you see it. Okay, so in one case you see the electron orbiting the nucleus. In the other one you see you can say the skin of the electron orbiting its center. Okay, in other words, here is what we call spin, like the skin of the top rotates around its center, and that's going to be spin. And then the other one is called orbit, which is when you have 2 separate objects, okay, and one object goes around the other, like the Earth around the sun. Okay, straightforward. We understand that. Okay, so what's the problem? Why are these people having so much difficulty in zeroing in on what spin is? Okay, and here's another continuation of that wiki article, and says the following. It says, for photons, spin is the quantum mechanical counterpart of polarization of light. Spin has no classical counterpart for electrons. Why not? I mean, spin is spin is spin is spin, right? The existence of electron spin angular momentum is inferred from experiments. And one of the prime experiments was the Stern-Gerlach experiment of 1922. They shot a bunch of silver atoms through a machine, and then had a magnetic field, an inhomogeneous magnetic field, which means that the particles are directed in one direction. There's more force on one side than on the other, so the particles are directed in one direction. Okay, they wanted to be able to control that. And it turns out that what they expected to see, according to classical mechanics, was a single line there. Okay, as you can see it, a distribution of all the atoms against the screen in a straight line. Instead, what they saw was two parts. One beam went up, the other beam went down. Okay, and so they related that to this property, intrinsic property of quantum mechanics that they say is called spin. So they never saw spin. Okay, they inferred spin. Okay, that's important to note. No observation. They deduced it. They inferred it. Okay. Okay. Nick Lucid, Curdy, guy who has his own show, the Crazy Show there, whatever it's called, the lunatic science. Well, what does Nick say? Well, he says he explains why the electron cannot have spin. Okay, spinning like a top. Okay? If those electrons have a diameter of 10 to the negative 18 meters, to be spinning with an angular momentum of 1/2 h bar, okay, the outer edge would be moving at almost 1,000,000 times the speed of light. So there you have this turtle of light, okay, and you can see the electron. I couldn't get it to spin 1,000,000 times faster, but it's moving faster than the turtle. That's the point, okay. So light would go slow, and the electron, the skin of the electron, right, would rotate faster than the speed of light. That's what he's saying. That's why they can't figure out what is really happening there, because the electron is a point particle, meaning it's even smaller than what he's saying there. It's like approaching zero, if not zero itself, because that's what a point particle is, just location and no body. And so he's saying that something so tiny would have to move so fast, much faster than the speed of light, that they cannot imagine the electron spinning like a top. Okay, I hope that sank in. Okay, that's what these people are saying. It spins, but it don't. Okay, so it spins, but it don't. Okay, so here we have another problem with spin, and that's that quantum top spins in both ways until you observe it. Remember, all properties like superposition and entanglement, it all has to do with the observer. And according to the catechism of quantum mechanics, once you observe something, once you touch it with your eyes or your hands, at that point the wave function collapses. And so before that, it's in both states. The cat is both dead or alive. And the top is spinning clockwise and counterclockwise. Maybe it's not spinning at all, okay? All at the same time. Until you observe it, until you touch it, until you do something with it. Then the wave function collapses. And if it was going clockwise, counterclockwise, and standing still, suddenly it collapses, to clockwise. And vice versa. You could collapse to counterclockwise, and so on down the line. So what we're talking about here is that it's got both or all properties simultaneously until you observe it, until you peek, until you touch it, until you detect it with machine or with your eyesight. God doesn't want you to discover his secrets. That's what it's all about. And so they keep investigating, researching what for the rest of humanity, for the rest of our existence, for what? If they already are telling you that they cannot peer into the invisible world of quantum mechanics, then what are they doing experiments for? To find more properties? What they need to do is stop doing experiments at some point and start explaining the experiments. And right now we don't have an explanation. What we have is descriptions, and the explanations are all irrational, and they say, well, yeah, it's the way it is. No, it's not the way it is. It's the way it is if you simulate everything with discrete particles. Then it's like that. Okay? Otherwise, no. Okay, so we need a new model. That's what it is. Okay, so what is spin? Well, I'm going to give you a shocker here, okay? Spin is just a bunch of orientations. And one guy tried to illustrate that. You can see the electron going around the proton. And all they're looking at is, whenever they measure, they look at what direction that arrow is pointing to. Okay, and they say, okay, here the electron is pointing, I don't know, northwest, and over here it's pointing southeast, and so on. That's what they're looking at. So it's the orientation, the tilt, okay? That's what they're looking at. And they call that spin. And it gets even worse than that, because what they do next really blows anybody's mind. They go in there and they invented quantum numbers, okay? Here you see them. I like this one, because the question of whether elementary particles actually rotate is ambiguous. No, it's not ambiguous. They're saying it doesn't. So it doesn't have that rotation like a top. So it's not, it's ambiguous, it's not. And then they say, why do they say that? It says, because they are like point-like particles. Yeah, if it's a point-like particles, meaning zero-dimensional, meaning no size, how can you conceptualize spin? And so what they've done is something even worse. They assign numbers to spin. You say, what do you mean you assign numbers to spin? What do numbers have to do with the physical spinning of a top? You spin a top, and you give it, oh, that's half spin. I'll call that a 1 spin. I'll call that a 2 spin, a -1. What is it? You're going to put numbers to the spin of a top? What sense does that make? So spin has some peculiar properties, I guess, that distinguish it from orbital angular momentum. It says spin quantum numbers may take half integer values, like 0, half, 3 halves, 2, etc. And so there I show you two spins that I created. I guess the first one is a half spin because it rotated only half. The ball just went halfway. And the other one's a -4th spin because it went the other way, counterclockwise, and ended up there. I mean, you tell me, what do they mean by spin? So we have a lot of properties for this spin. It has several types of spin before you detect it. It's just orientation or tilt. And then it's got numbers assigned, I guess, to the different tilts. If it rotates only halfway, then it's a half spin. What is this? So it's got all these strange properties. And then, of course, a guy like Matt Dowd, supposedly a mathematical physicist, he comes out there and says, oh, by the way, we have no idea what spin is. Okay, but it turns out that they say they don't know what spin is, but they use the word spin. Why did they put the word spin? If they don't know what it is, they should have called it X. The property X. Then it would have been it would have been dubious. A lot of people would have thought, oh, okay, what does he really mean by X? But when they say spin, everybody says, oh, I know what that is. And even though they don't know what it is, that's how they use it. Here you have fellow James Lincoln, and he's from UCLA. He's got this video on the internet, YouTube, and says, how do magnets work? Okay, and he says, could it be that the electrons orbiting the iron atoms are the net cause of magnetism? That is, could it be that circling electrons are causing the magnetic field? In 1915, Albert Einstein von der Haas ran an experiment to check that it was the orbiting electrons that caused magnetism. The results were negative. In other words, it wasn't the angular momentum, the Earth going around the sun, that caused that caused attraction, that caused magnetism. But he continues, he says, later on, it was discovered that electrons had a property called spin. And there you can see him spinning the ball. Okay, what is he talking about? He's talking about spin. He's talking about top type of spin. That's what he illustrates. He says that is that the electron was spinning as it circled the nucleus. So what is he saying? He's saying the electron is spinning like you spin a top. He didn't qualify it in any way. Okay, so he's talking about spin like a top spin. There you see it again. See how he twirls the ball? And he says it's the alignment of these electrons spin that results in the magnetic properties of iron. Okay, and he never goes beyond that. And he started saying he's going to tell you how magnets work, and that's all he says. That is the entire. I mean, you can just skip everything else because that's essentially what he ends up with. He says it's the alignment of these electron spins that results in the magnetic properties of iron. And so I got a lot of questions there because I cannot imagine the mechanism that he's trying to talk about. Okay, there you can see him spinning again. Okay, so I've got a problem because here I have two balls, okay, so this one's spinning. You can put them both clockwise, like he showed there. One clockwise, the other one counterclockwise. Do it any way you want. I don't care. Do it any way you want. How does this one attract that one? How does this ball attract this ball if there's nothing in between except what? We have to think of it as some interconnection there, elongated object. We've got to think of it like that, but they don't illustrate it. They put the balls and they say, this one affects that one. I want to know the mechanism. What is the mechanism? They say, well, you got to think of it as if. You see how they're doing it? So they're cheating because that's nowhere to be found in quantum. It's nowhere to be found in the standard model. Okay, but that's how they illustrate it. That's how they mimic it. Okay, and you say, okay, what is that ribbon, that thing that connects the two electrons or atoms or whatever? And that's where they say, well, you only have to think of it as if. And that's the end of it. There's no more than that. So yeah, the big problem of quantum mechanics is action at a distance, specifically the force of pull. How do you pull from a distance? How does this particle affect that particle from a distance without any physical mediator? The guy who does that is introducing spirits in that same space. There is no other way of looking at that. You're using black magic to get your theory across, your mechanism across. How does a rope model do it? Well, ours is simple, okay? Yeah, how a magnet attracts another. You have the threads, and they do spin, okay? They spin clockwise or counterclockwise. And when they spin both clockwise, and then they're attracted. And when one of them is turned around, you'll see this in a second, we'll have repulsion. Why? Because you have blue against blue, meaning clockwise against counterclockwise. That's what happened. Now they push each other away. So it's very straightforward. You see the mechanism. You don't have to imagine it beyond what you see there. Okay? So if you want to know why two magnets attract and repel, there you have it. You have these threads that are swinging around that we cannot see or touch. Okay? So there's no purpose in running experiments. We have to explain how Mother Nature is doing this trick. Okay? That's all we have to do. And yeah, it's one of these things that we're not going to solve by going to the lab. Okay? Okay, so what are my conclusions about this so-called spin? Here they are. Okay. Spin is another mysterious property that quantum particles enjoy. Okay. Together with what? We had entanglement, we had superposition, decoherence, the cat, Schrodinger's cat, you know, he's dead and alive. We have all these little properties, and this is just another one of those mysterious properties. Why is it mysterious? It's mysterious because they cannot explain action at a distance. You can't do that with particles, and that's what quantum is. Quantum means particle, means, you know, it's a particle theory. You cannot explain this with discrete particles. That's what they have to abandon. But the mathematicians love particles because the particle is simply a location. It's an equation that puts a value there, and they can put that in an equation. If you put a ball, they can't put the ball in the equation. They have to put in a number. So they put the word energy, or they put mass or force or whatever, and they have values for this. They can play around with that in equations. And so now you're going to tell them after 100 years that there are no particles, no wave function collapses. Is that what you're going to tell them? No, of course, they're not going to buy it because it destroys their entire religion completely. And yeah, I'm saying religion, that's the correct word. Because it's a religion because all the explanations that they're giving you are irrational. And they believe in them. And they vouch for them. They say these theories, these mechanisms have been proven. And when you say, well, how do you prove something you cannot even imagine, which is irrational? They say, well, that's philosophy anyways. And that's it. And that's the end of the story for that. Okay, so mysterious. In this case, very mysterious because they cannot even describe spin. I mean, if they could at least describe what spin is, but they cannot. They cannot define or describe it. They cannot. Okay? And of course, then they cannot explain it. Why? Because it's an irrational mechanism. They're using black magic. They're saying that a zero-dimensional point particle has no body, no size, no diameter, no radius, no dimensions, is spinning. So what is it that is spinning? Please draw it for me so that I can visualize it. I cannot imagine a zero-dimensional nothing spinning. And that's what these people are saying. And then they assigned numbers to spin: half spin, 2 spin, 3 half spin, and so on. Negative spin goes in the opposite direction, I guess. Not direction because it's not spinning, so I don't know what negative spin means. I mean, negative half spin, what can that possibly mean? It just means it's got oriented in the other direction. It was clockwise spinning, counterclockwise. I don't know. You figure it out. I can't help you there. Particle spins in both ways until you observe it. That's the wave function collapse. At that point, all properties condense to one series of properties. Okay, but a quantum particle has no size, so what is spinning? But let's use the common notion of spin that everybody has when explaining. So you're going to use it anyways as spin, and they're going to use that word spin because everybody understands the word spin. They think they know what the mathematician is talking about. And you just saw James Lincoln there saying, yeah, it's spin. And he still, even with his little spin, which is not spin in quantum mechanics, he cannot explain attraction. He just says it is so. When they're spinning in the same direction, the magnets attract. Okay, so how does the electron over here spinning have any effect on the electron spinning here? And that's when they turn the lines of force, magnetic lines of force, which they say do not exist, are not real, that they're put in there just to explain something, but that they don't exist. So they're saying this ball affects that ball from a distance by what? By black magic. So yeah, it's a big problem. And magnetic attraction, because the electrons of the atoms on each magnet spin. So that still doesn't explain action at a distance. And so the question is, so what is the mechanism? What is the mechanism not only of magnetic attraction, what is the mechanism of spin? We still don't know what spin is, but everybody knows because everybody simulates it the same way by twirling a top and saying that's spin. You figure it out.